Hello everyone, my name is Ramal and today I'll be talking about my thesis project on visualizing interpretable decision boundaries of deep learning models. Before I begin, I'd just like to thank Dr. Helen Paik, Dr. Chen Wang, and Hector Wu for supervising, assisting, and motivating me throughout the whole project. So to begin, let's look at a couple of examples to explain lack of interpretability when it comes to deep learning models. In Cooper et al.'s work on predicting pneumonia mortality, we see that the neural network model has an accuracy of 0.86, which is good. We also see the prediction pattern that if a person has asthma, then they have a lower risk of pneumonia. What we don't see in the data used for training is that the person's doctor recognizes that they have a high risk of pneumonia, they perform aggressive treatment, and that is why the prediction results in a lower risk of pneumonia. This highlights that a more interpretable model could reveal important but surprising patterns in the data that complex models often overlook. When engineers have a model that they have produced, popular questions they usually have include: the accuracy is low, and we know that there are errors, but what were the errors? Why were there errors? What data did the model struggle to classify the most? How did the model learn the data to classify the results as is? Basically, what we go through is this process. Neural networks are a black box in which we feed input and get output with little understanding as to why this particular input led to that particular output. We have no idea what's going on in between here, and this is the problem that we face. Keeping this in mind, let's move on to the introduction. Deep neural networks are very popular and powerful and have accomplished numerous achievements in various areas in recent years. Such areas include image classification, speech recognition, and classic games such as Go. Due to this success, deep neural networks are being utilized increasingly more and more in a vast number of applications. Despite being so powerful and having the capability to outperform humans in various tasks, deep neural networks are often evaluated as having a lack of transparency and interpretability. As explained before, the decision-making process of deep neural networks remains a black box, meaning it is very difficult to explain the path a model has taken to come to a decision. As well as this, the model quality is challenging to evaluate, especially for the case when the spread of application data varies from that of the training data used. In this case, the normally used precision and confidence measures are not adequate enough to disclose model behavior on the applied data. There is an immense amount of related work available on this topic area. I will just go over a few right now. A common approach is to find examples or prototypes to guide decision making, which is along the research line of case-based reasoning. Case-based reasoning involves solving a new problem by reusing existing similar examples and knowledge of that situation. An example of case-based reasoning being applied can be seen through Brienne et al.'s work in their 2011 paper on prototype finding. They use prototypes as a tool for better understanding a dataset, that is, making it more easily human readable for users. The example-based classifiers from this work have been shown to achieve comparable performance to non-interpretable methods while offering a condensed view of a dataset. In our work, we use this case-based approach to improve deep neural network interpretability by showing similar examples in training data for users to interpret predictions made by models. When a classifier makes mistakes, the engineer has little information as to why the classifier made the mistakes and how to improve its performance. Currently, the resources available are to increase the training dataset size or to examine errors manually, so diving into the trial and error process of seeing what features are missing or what training data might be missing and retraining the model. This is very time consuming. To work towards this, visualization is used to examine features extracted by hidden neurons in deep neural networks for users to infer the relationship between a classification decision and these features. In our work, we also use this visualization approach. In this work, we also make use of some previous work done by Dr. Wang and Hector, where they proposed a method to enhance users' understanding of a shared deep neural network model by providing a small set of training data that characterizes the model's decision boundaries. These data points are informative for users to infer how a prediction is made in relation to them. They employed a max margin-based approach to select the most representative training data that largely contributes to the forming of the decision boundaries of a model. The number of nodes shown in the boundary indicates how ambiguous the model is. The more nodes, the more ambiguous the model. You will also find that if a training point is mislabeled, it is likely to appear at the decision boundary. The decision boundary should help users better understand the similarity and dissimilarity of features embodied in the boundary and in the test data. The separability of decision boundaries can also reveal the weakness of a model. They call these boundaries interpretable decision boundaries, and an example can be seen right here. There are many more related works that exist, included mimicking a complicated model using an interpretable simple model such as a decision tree, the sample perturbation approach, which attempts to identify features leading to certain predictions in image classification, and similarly, influence functions that are used to identify the most important training data leading to certain prediction. The only difference between sample perturbation and influence functions is that the sample perturbation is used for image classification. Taking this into consideration, the main proposal of this thesis was to work towards a visualization tool to enhance the interpretability of deep neural networks' decision-making process, and provide answers to some of the questions that I mentioned at the beginning regarding the black box workings of deep neural networks. The tool will work towards helping users to more intuitively infer how the decisions are made according to training and test data, as well as the decision boundaries and k-nearest neighbors of models. This type of interpretability could also allow spotting potential weaknesses of models and improve the method of model comparison by allowing a comparison to be made on model behavior rather than numerical statistics. The figure presented illustrates the system architecture and the workflow, which represents the proposed framework. The framework assumes an existing machine learning processing workflow that produces a model. Our own interpretability framework takes the model as input. The feature extraction is applied on the softmax and hidden layer of the model. The softmax layer is the final layer of the model, while the hidden layer used is the second last layer in the model. Most datasets used in deep neural networks are high-dimensional. In our case, we use the deep neural network output of the MNIST dataset, which is in 10 dimensions. The MNIST dataset consists of 60,000 trained images and 10,000 test images of handwritten digits. To overcome the challenge presented by this high-dimensional data, we use dimensionality reduction. This is because we know that anything over 3 dimensions is hard for humans to interpret. In order to perform the dimensionality reduction, we use the TSNE algorithm. This is an algorithm that visualizes high-dimensional data by giving each data point a location in a 2 or 3 dimensional map that can be displayed in a scatter plot. So our dataset will be transformed from 10 dimensions to 2 dimensions and allow for a better visualization. Through this, users are able to see the clustering of the model's data points. Each of the clusters formed represents the most similar data points which are learned by the model. We use this method in order to enable users to view these as an example to infer the positioning of new data points within the model as well as spot errors. Another functionality we use is to perform a nearest neighbor search. This is to allow users to view the nearest neighbors of data points for a model. When analyzing the neighbors, users can deduce the prediction of a new data point within the model using the neighbors as an example and explicate the relationships between data points and that the model has acquired. Users can also spot weaknesses in the model if the neighbors do not seem to match well with the expectations. As mentioned before, we also do boundary extraction. The boundary traversal in the tree can help users better understand the classification results, as the nodes in the tree show examples of data points that the model considers most ambiguous in making decisions. It can highlight weaknesses of the model. So as we can see already, these mechanisms provide some answers to the black box workings of neural networks. The server-side components of the framework are generated using Python's Flask library. In addition, the client side consists of HTML and JavaScript with D3.js, which further contains various SVG elements that are used for the different visualizations. Flask allows for fast and easy setup with efficient passing of variables and data between web pages, and D3.js produces dynamic interactive data visualization in web browsers, which is what we were trying to do. So, taking the framework into account, we developed Deep Explorer, or in short DEX, which is a use case implementation of the framework. I'm just going to take you through a demo of this initial version. Here is the home screen of the application with the TSNE visualization of an MNIST trained model. We can see the clustering of each of the classes for the training data points and the relationship between each of the predictions made by the model. The legend on the right-hand side shows the relevant colors and labels of the different classes of the model. When users hover over the points, they can see the corresponding image of the data points, which improves their understanding of the relationship between each of the points in the clusters. This is to fulfill the main aim of interpretability, as the users will find it useful to know what each of the data points actually looks like. We have a lot of functionality available that provides users with different ways to use the application. This functionality includes a help menu, which can be found here. The help menu can help them figure out how to interact with the system when they first arrive on the page. So the help menu includes different information about each of the features that we have. Users also have the option to view different layers. As we discussed before, we visualize the softmax and hidden layer. They have the option to choose between different models, change the number of neighbors, upload a test data point, and show boundaries. So as I mentioned before, we allow users to view the decision boundaries of the model. The decision boundaries presented is a region of the model in which the output label of a classifier is ambiguous. So the decision boundary should help users better understand the similarity or dissimilarity of features embodied in the boundary and in the test data. The nodes that are connected together are the nodes that the model finds most difficult in distinguishing. So for example, the model finds it hard to distinguish between this data point and this data point. To improve their model, users can use the data, especially in the congested area, where nodes are found close together, as a seed to fine-tune the model. So they can take these data points and create similar examples with correct labels and feed it back into the model, retrain it, and that will probably improve the model even more. When landing on this page, it is expected that users will not know what decision boundaries mean. Hence, there is information presented to help them figure out so. So this is basically the information that I went over before, outlining what decision boundaries are, what trends users can look out for, and how you can use this to improve their models. So if a model has a point in the decision boundaries, it is likely that similar data points to this may be misclassified as the model finds it hard to distinguish these points from other points. So just keep in mind this little data point over here. If we were to feed a similar example to this to the model, it would most likely have trouble classifying it. So just keeping that in mind, we'll go back to the main screen by hiding the boundaries. So upon clicking on a data point, the data point's k nearest neighbors are highlighted, where k is set to 5 by default, and users have the option to change the number of neighbors using this menu over here. With this feature, users can visually see the relative distance of the points in a two-dimensional mapping gained from the higher dimensional space. The neighbors are what the model found most similar to the selected point. When selecting a data point, users can further inspect the data point's k-nearest neighbors by clicking on the Explore KNN button to see a more detailed display of the raw images and labels corresponding to the k-nearest neighbors. So that was the chosen point, and these are the k-nearest neighbors of that point. This will be useful in the case when a user wants to better interpret the relationships and similarities within decisions made by the model. This makes it more intuitive to the user which features of the images may have led to the classification or misclassification of a data point. So we'll just reset the visualization here. So users can toggle between showing the data points of their choice. This functionality allows toggling between showing only the training data points, the test, or only the test data points, or both. They can also do so with the individual classes. So clicking on any one of these, they can toggle on and off the corresponding cluster. So that is the test and train points gone for the pink cluster, which is 5. So the application allows the spotting of two kinds of errors: training errors and test errors. Training errors refer to the incorrect predictions a model makes on the training data. This training data has been utilized to actually train the model, and this essentially does not imply that the model, once trained, will have 100% accuracy. The second error is a test error, which is the error received whilst running the trained model on new, unseen test data. This data is used to reveal the true accuracy of the model. Now, to spot these errors, you can either look at the labels within the table presented in the k-nearest neighbors, explore k-nearest neighbors mechanism, or you can look for a point that has been put in the wrong cluster. So a color that is in a cluster which is not correct. So there is no training error presented looking at the train points, but if we switch over to the test points, we can see two train errors, one here and one down here. Now looking at the second one that we just noticed, if I click on this point, now remember the point that I told you to keep in mind from the decision boundary? This point is very visually similar to it and has been misclassified. The true label of this point is 4, and we can see that because it is placed in the 4 cluster. But the model labeled it as a 0, and we can see that because the color of it corresponds to the 0 label. Now, us as humans looking at this data point will think, this can either be a 0 or a 9 or a 4. Now looking at the k-nearest neighbors of this point, if I just extend it to 15 to gain a better insight, we see this is exactly what the model thought as well. It has neighbors both in the 4 cluster, the 0 cluster, as well as the 9 cluster. So this is a weak point in the model, and we can even see that in here. So these are all of the points that the model found similar to the point that we were looking at, and this is what it used to make the decision. Now users can then improve their models by feeding similar examples of these k nearest neighbors labeled correctly. So increase the number of examples, retrain the model, and that should help it better differentiate between these classes. Now if I reset this again, we also implemented a feature of uploading a test data point to show its k nearest neighbors. So these are all of the test images. If I just choose one random one, open, so it will show an instant visualization of exactly the path the model takes in making a decision depending on the input data. So that was the point that we uploaded, and those are all of the k nearest neighbors that it used to determine the positioning of this new point. Now that currently the test points allowed to be uploaded are from the existing test data set only. Last but not least, we have the model comparison feature. Now, the model comparison feature allows the rendering of a side-by-side comparison of two different models. Users have a variety of options available to choose from in the comparison mode, so they have a permutation of different comparison modes, so different layers and different models. All the features mentioned before are also available in this visualization mode. Whatever action a user performs on one of the models will render the same action to be performed on the second model. This is basically an interactive visualization that allows users to carry out and interpret model comparison more efficiently. This makes evaluation of models much easier by dealing with the model behavior rather than the numerical values. So we can already see through the visualization clustering that the model on the left is much better as it has a neater and better formed clustering, whereas on the right hand side the situation is not as so. So now to support this, users can view the decision boundaries. So we'll just click on that, so then we can get a side-by-side comparison of the decision boundaries of both the models. So it will just take some time to render. So looking at this, our initial thought is confirmed by seeing the boundaries, because the more nodes in a boundary tree, the more ambiguous the model. Now this will be very useful for the case when you have two models with very close accuracy levels. In traditional cases, you would go with the model with the higher accuracy. So in traditional cases, you would go with the model that has a higher accuracy, just because that is how traditional numerical comparison works. However, if you were to compare models using this visualization method, you may find that the one with the lower accuracy actually generalizes to the data better. And it just happened to be luck that the test data set that you used on the model worked well, but if you used another test data set on the higher accuracy model, it would not be the same case. So all in all, this insight cannot be gained through analyzing the traditional numerical statistics. Now, all of these implemented features have been developed with the aim to mitigate the black box phenomenon of deep neural networks. To evaluate the effectiveness and efficiency of the use case implementation, we carried out some usability testing. We invited 13 participants having basic understanding of neural networks and machine learning for a user acceptance study. We aimed to answer the following two research questions in this study. Determine if the DEX application allows users to gain a better insight about the DNN model they are exploring, and evaluate how efficient the user interface of DEX is. So the first research question would basically provide us the answers as to whether we have successfully fulfilled the aim of improving the interpretability of deep neural networks. And the second question would evaluate the usability of the use case implementation. To find the answers to these questions, we designed 8 tasks that each participant needed to complete. The tasks were divided into 2 parts. The first part was to complete the task, and the second part was to answer some follow-up questions. The first part of completing the task allowed us to gain insight into the usability of DEX, whereas the second part, answering the follow-up questions, highlighted the usefulness of DEX in trying to satisfy the aim of improving the interpretability of deep neural networks. After users had completed the study, we also gave them a post-questionnaire to fill out, just in case we had missed any insights we could have gained. These are the tasks that were carried out, and a few information is presented about the metric we were trying to gather and the average timing of the tasks. The metric that we were trying to gather came from the actual follow-up questions. So the participants took longest to carry out task 4, which regarded finding a train and test error. This was due to the fact that they actually had to spend time looking for the train and test error, and they also struggled most with exploring decision boundaries, so task 6. And this is due to the fact that a lot of people had questions regarding the decision boundaries, as they came in with a pre-contextual concept that decision boundaries were actually the gaps between the clusters in the models instead of what we were actually presenting. Having a look at the metrics, we can see that most users found the features implemented to be highly useful in interpreting deep neural networks. The metrics that show lower scores, so the 12 out of 13, were all given by the same participant. This one participant did not understand the concept that was trying to be conveyed due to the lack of knowledge in the neural network and machine learning domain. Hence, they were not able to give an opinion on whether they found the feature to be useful or not. All participants on average spent the least time on task 3, changing the number of key nearest neighbors being explored, and task 7, looking at a different layer, as this only involved changing menu options. Although a prerequisite of participating in the user study was to have a basic understanding of neural networks, machine learning, and clustering, we had a wide range of knowledge levels within our participants. We asked the participants to self-rate their proficiency and experience on the topics. According to this, the response time for every participant is shown in this figure, with the participants being sorted in decreasing order of their experience with neural networks for each of the tasks shown in the previous section. Interestingly, participants doing research in the domain of neural networks asked many questions while performing the tasks, resulting in an increase in the total completion time. For example, participant 7 and participant 10, who were the most relevant researchers, spent the most time on task 6 on decision boundaries, while querying about the algorithm used for calculating the decision boundaries and what they were trying to tell them. Participant 1 had the least exposure to neural networks and had the most queries throughout the task, resulting in the longest completion time. Experienced participants were positively surprised by the immediate effects of the visualization and being able to find out vital information about the models. On the other hand, many of the users with limited knowledge of neural networks also asked questions, for example, what the dataset was, what the visualization was showing, while reading the help information spread throughout the application. After learning about what was going on, they were also positive about the tool and the aim that it was trying to satisfy. Presented here are the results of the post-task questionnaire. The goal of these questions was to get the user's experience and opinion during the user study and capture any insights we may have missed. The first 10 questions are selected from the Software Usability Scale questionnaire. This scale is usually used to evaluate systems as such. The presented result of the participants' answers to these questions demonstrates the effectiveness and usefulness of the proposed system. For the first four statements, the lower the score the better, and for the remaining, the higher the better. Out of all of the results shown in this table, 11 out of 12 statements achieved desirable scores. Statement 1 received an average of 3.22, which was borderline, whilst we were looking for a lower score. This response can be linked to the observation that users found the system a little difficult to learn at the beginning due to not being able to navigate the help menu and being able to differentiate between menu items and buttons. They also struggled understanding the decision boundaries. Like I said before, this was due to the fact that they came in with the pre-contextual idea that the boundaries were actually the gaps in between the clustering of the model. Now I'll quickly go over the demo of the application version after the feedback was taken into account from the usability testing. So this is the home screen of the application after the updates were made. So we updated the design of the menu options and the buttons because users found them to be a bit indistinguishable and could not figure out that they were action items at times. This was done by adding more styling, like shadow to some buttons, outlining of menu options, use of better colors, and use of actional verbs in all the action items. So before it was just model. Now it's changed to choose model. The toggles were changed as users did not know that they could use the two buttons up here to toggle between points. So they were made as two separate buttons over here where they could actually click it to hide and show the points. Many people went to the help menu to look for information that previously we didn't have. So this was added in there. The help menu was expanded to include more information, especially the items that the users did not find in there before. The decision boundaries were renamed to ambiguity trees. As we discussed before, a lot of users came in with the pre-contextual knowledge of decision boundaries and had trouble adjusting to the new idea of them. So when we actually think of the boundaries that we presented, they actually show the ambiguity of the tree. So we changed the name to ambiguity trees. Now, clicking on this, you will notice that we also added in a loading mechanism. We did not have this before, and users were confused sometimes when they were waiting for elements to render. They thought they hadn't clicked something properly or the application wasn't working. So to increase the feedback given to the users, we added in a loading mechanism. The information icon was changed as during the testing, users found it hard to spot it in the corner down here. So we changed the positioning, and instead of having it as an info icon, we actually added the title of what are ambiguity trees so users know exactly where to go if they're struggling with finding out information about this. As we do understand that when users come to the page for the first time, they won't really know what ambiguity tree stands for. This information is also available in the help menu. Now, going back to the original view, we also got the feedback when viewing the k nearest neighbors of a point, the table that is presented in Explore KNN, where we go on to here, users found the single column to be really annoying when they had to constantly scroll down to view all of the rest of the images. So we changed this to render according to the amount of neighbors selected, and we also added in extra information regarding what the model labeled the chosen data point as. This information was found to be missing when users were trying to explore how the model made the decision. They questioned what the model actually labeled it as, but we did not have this information presented anywhere. Hence, we had added it into this section. So as we noticed, most of the improvements made are using the regards the actual usability of the application. Users did not suggest any improvements with the in terms of using methods to improve interpretability. They found them to be pretty satisfactory. So to conclude, a deep neural network interpretability framework and its use case implementation named DEX was introduced. The framework aimed to help users have an improved interpretability of deep learning models by allowing the users to examine various example cases of the model's behavior. We evaluated the idea with DEX using the MNIST dataset and a user acceptance study. The evaluation results demonstrated the effectiveness and efficiency of the different means of DEX on improving the interpretability of deep learning models. The framework also demonstrated a better way of carrying out model comparison and evaluation. Thank you for listening to this presentation.